So I'm going to do this one up before I cash in. I actually got a headache after this one. Too much coffee, sitting back, smoke cigarettes. Not great for you, Tony Stark. The best thing we ever made. You're in the Sprinkle Factory. I'm talking about you, don't worry. Anyways, we'll be setting into this watch later category here for a minute. With things to be and come in the future, we got a fair bit of work to do, boys. Team, A-team. A fair bit of work to do. But we're going to do this because I want to go through this. Now, we might get back into doing some of this other stuff later, and I have a few more of these to go through first, but I love these headings, right? We got the, we'll go the other way. That's, should have been the other way. Maybe it come off at the bottom. I don't know, maybe I clicked on it or something. Alright, I actually want to start here. Okay, the product of... What was I going for here? What was he got on the board here? This may not be the one. I definitely want the discussion of the chain rule, because we can make this math whatever we want. And remember, we actually want to keep the tone into it of The Apprentice, because it doesn't seem like we're really doing it here from the classroom to the student. And as you walk your way up this multivariable function, you would say that the distance, rate, time, word problems is the ASVAB version of the applications of slope fields, right? And we can break down lots of many different variables of useful things to dealing with the bunny rabbit, right? We actually want to catch a bunny rabbit. This is heavy duty math. We could make it micro coulons, and we could do anything else with it. But we're going to have to deal with this in the classroom of some issues that hopefully if you watch some of this you'll start to pick up, of a quark asking questions to the teacher about the world and population growth and decline, harvesting population growth and decline. And this will be things like I wish I had the conventional name. We might even get up to it up here in a minute. Power functions. Like, it's a thing that it's part of the room. It's just going to be, I'm the one that's supposed to do the board work here. You're going to get into which one of these versions, whose laws, about the basic V's, Q's, ABCs of it all. And that's this, the finding the dominion, right? We want to find the dominion function, the fun version of the imps in the whole current, not necessarily solving logarithms. And we want to use this log equation with exponents. Guess what? I'll be that exponent for you, logarithm. Solving exponent equations with logarithms. Also super critical, and I'm going to keep them tight like that when I go running it like this. But these are obviously quite comprehensive about what material we'll be dealing with and how I have to break that down. I might deal with it a little bit different, but like I said, you're going to have to get into it with Salty Rabbit, the knife hand. You're going to have to get in there with the knife hand, unless you want to run the whole book like that. Good for the way they're doing it. This is only a subset of their information of pre-algebra, advanced algebra, and other things like that. We'll be covering subjects where they're doing the same equations. You'll even see it in the loop over their time series of, like, after 4 years, go back to the beginning and try to hit it again. Maybe run it in the lecture or something, and you'll begin to pick up on that example inside here, or getting that those little photos and stuff. Base properties of trigonometry, like there's a base, there's a trigger word that says this is an army barracks, right? That this is home base for the logarithms. Graphing the sine and cosine, I think is pretty much straight down the pipes, isn't it? Okay. How to graph tangents and cotangents. Well, what's a tangent if the sine and the cos? Oh, I see what you did there. And I want to be real sure that we graph that in a way that, hey, everybody here at the lodge and how we determine a function is cool with that idea, and or how we have to handle a parallel to that to be able to Alice and Bob it in such a way that the tangents and the how to graph the cosecant and secant, in the way that there's a tangent, there's a way to deal with my secondary and or excuse me, some secondary I'm watching as a tangent, and of course my secondary that we would send out in operations alpha, beta, causal, gamma, whatever. Um, Introduction to using trigonometries, and this will be a good one for the rabbit snare. I think get the parts going, how to provide trigonometry identities and things like that. We're looking for what triggers are logarithms because these are really close to the same stuff, and if you're not careful you'd be running through the same material, and it's a hard thing to explain. How to solve trigonometry equations, you got to get the rabbit in the trap. You gotta be able to have the mechanics of any trigger, the one I want it to do for rabbits, and then making sure that over there, even though if I got one, it doesn't necessarily mean it's always going to be the design in which this using this half angel half demon formula here, as you do, um, would be how I would integrate that. Because look at it. Let's take a look at what we got at the board here. You're gonna, especially in your books, if you were running something like this, how to convert a polar coordinate to a rectangle coordinate, right? A real location on Earth with the logarithms, all this setup to get through there. And how strong is your heart? I thought this was a fun way to deal with the question and the problem of grammaticing an issue. That's a real SCV right there. Book graphing, we're going to pick up that book. You realize how heavy that book is right there. Two masses, a pulley, and an inclined plane. That's me and you, brother. There's one rope and one pulley, and we go round robin. Now, we could fight for it. We could. We could get into the 10 to the 78 iron and the pipes. Well, I suggest we both drop a doge on the moon, right? Or Mars. And I think that's fun because it changes the way you deal with the gravity to say the torque on this bolt, because Bones made sure I got this one in here just as a fundamental. They don't need to necessarily line up like this, but there's going to be a structure, and they're going to be two vastly different types of things. I mean, we got some big differences inside here to how I might want to line up the structure. And of course, we could have done torque and friction and all the bunny stuff, and getting in there and going through go all the way to the bottom, climb all the way to the top, try to find which ones you work. Because even though I didn't hit it in here, it didn't mean it. As soon as you ran past this and saw something, you didn't FMA the YouTube pressure for the density of an object underwater, and you could tell he was as a teacher or something. The hanging hanging a beam, right? Yeah. Introduction to force. I thought this one was straight down the pipes. I think it's worth what it is because we'll get to one higher of introduction of force, and basically explaining to you that this isn't the answer, and if you do the math with it, I shouldn't need to force you, right? Because you just pick it up. The hanging beam. How old are you in seconds? I like this because this is that not just a good basic to have, but also serial rate, not a serial number on that M1, bud. And that's that memetics, right? We're just doing it in one dimensional. We'll get into two dimensional here in a minute because it's in every one of these equations. I want to take a special moment to talk about that. So I couldn't because they weren't in the lineup as I was climbing. Do we do these? Potentially. Maybe not. Maybe I clip them out later because a lot of the material, well, good, and object in motion should be covered regardless of whether we have kind of really done it or not. Right? Because those objects are going to stay in motion. They're going to act like some of these other fields we're doing, and it would be a good way to touch on the material. Two blocks tied together. Yeah, okay. Work lowering an object. Now this one's important. There was a lot about the slope, running down a slope. Is he talking to a student? Is he talking to himself, getting away from this? Slowing down the merry-go-round? Is he talking about the student? And those are really cool ways to talk about this clock, this mod, this period. Why Newton's the big G in here? Because this form comes down to the gravity, which could be anywhere at any point on any time topology ever. And you got to kind of realize, that's the difference of, you could be in free fall, but also free fall is this orbit that I have in here, which might be relative to the center of mass about what objects and how much and the do. I wasn't really sure about this one, but I got a bit of the pie chart. It's a huge lensing problem on certain objects, their periods and differences, so I'm sure it'll be a great way to cover it, but I don't know. We might change it out a little bit. I might have to do some name things because it's good. It's good. I don't usually like to argue with amps and ohms and Gauss there, but in that way, if it was Gauss and they really did the math and you weren't real careful about it, it's something to it's something that you have to really consider. Um, I thought this one was just fun for any seals that get in there. When you dive past the first atmosphere, it's like that's that. We train you for the first atmosphere, all the way to the second atmosphere, and that's kind of the bandwidth. When you are out there, that's the kind of pressure you're going to be feeling about that. Mimetics in 2 dimensions. This charge in field, and these are some beasts. So we might have to do some different things with it, as much as not necessarily chop it up because he had already. He'd done a lot of it. He almost had 2 copies of the same exact file running through here. You could tell he'd been doing things with the logarithms of the standards of somebody watching his YouTube file because he's doing the pressure of YouTube. Um, I like the reference here. I think it's pretty straightforward and useful. It might be necessary to deal with like currents and timelines and adjusted systems. Um, Force and potential energy explained. Like I love the process. We can use that framework for it. How to get the electric field from the potential, how to get the potential from the electric field. Here you are standing next to me. The zaps are the zaps. You invert the numbers and figure out how they work for you, and you invert that system to kind of get that tangent under control. Try to get the quarks in the room and stuff like that. Manage it best you can, bar at the bar. Um, the resistance depends on the frequency. You usually say it's the teacher here. It depends on how many times you guys kick in this room is where force starts to be necessary on the frequency of 11111, and it's a great way to again walk them through the process of these would be the points that I started to add into those values. Single slit, diffraction. We want it to pass it. I would turn this up here and shoot it at the classroom like my designs, but that might be relative to how many of these you have to organize, because then you could be like, well, he's a teacher shooting at you. The diffraction of that is still correct to the, like if it's a laser beam shooting through there, you'd want a diffraction beam that's not so much information while dealing with that of a portional model as to students like kicking that kid up and getting the interference on the single slit, or the single slit is what I wanted. I thought there was another one. I wanted the single slit uh, interference with then to build to the 2 slit like I do my like I did those Michael Van stuff. So that's my note. I'll catch you on the next one.